Hey guys, what's up? Once again, my name is Cesar Escajeda, and I am one of the GEARUP tutors over at Indian Ridge Middle School. For this video, we're moving a little bit forward, and I'm going to talk about an algebra concept you're likely going to run into or may have already, and that's going to be exponential growth and decay. It sounds a little complicated at first, but I guarantee it is an easy learn, and it's one topic that really has a ton of applications in everyday life, especially a lot of careers, and particularly these days with the current situation we're all dealing with, which I'll go into detail about a little later. For now, let's get started.
When you see the word exponent, you probably think of something like this: 2 squared, 3 squared, all these numbers, with the smaller number up top being the exponent. It applies here. Exponential growth and decay are the titles given to a series of functions that describe how things increase or decrease at ever-enlarging rates, or rates that move in non-linear ways. With linear lines, it's a straight diagonal path depending on the variable plugged in. Exponential rates are different. What this means is that exponential variables follow patterns that don't just go along a straight line. They increase or decrease more and more at each interval, looking eventually like a large loop on a graph, because the numbers get larger and larger or smaller and smaller each time. I'll explain.
This table, notice the patterns. The x values increase by 1 each time, but notice how it affects the y values. You start at 3, then 6, then 12, then 24, and so on. Not a typical standard linear pattern, right? This right here is an exponential function of growth. Y equals 3 times 2 to the x power. And it's a great example of growth exponentially. See the pattern? Here you notice the y doubles each time. Times 2, times 2, times 2, and so on. So what if I threw something like this at you? It's the exact same setup, but now we're looking at a form of decay. So each y multiplies by an exponent of 1/2 every single time. And you see that the y multiplies by the exponent of 1/2, and it's getting smaller and smaller each time. So the function looks a lot like this. Y equals 3 times 1/2 to the x. These numbers can be applied when looking at graphs and patterns as well, which goes along with the big concept we're talking about today. To show you a little comparison, here you see a graph that follows a linear approach, one that you guys have probably seen quite a bit. And up here you see the function, y equals mx plus b, right? Now, take a look at an exponential growth and decay graph. So here you notice the difference. So up here you see the parent function, y equals a times b to the x. With every interval on the linear, it's a uniform change, meaning the pattern is the same each and every time. Exponential growth and decay is obviously different. With each interval, the rate of increase or decrease gets larger and more visible. So there are a few rules to this, and they do help you quickly identify what type of function you're dealing with. Obviously, growth means increase, getting bigger. When the function is exponential growth, the value of the number affected by the exponent, or b, must be greater than 1. So in the example that I used previously, you can see that the b value here is 2, which is obviously bigger than 1, right? Decay is the opposite. With decay, the b value needs to be less than 1, as you see here. Using the example we used previously, you can see that the b value in this equation is 1/2, again, less than 1, so it works. With this, you can quickly identify which is which just by looking at the number or by reading a word problem and figuring out what your exponents are, which values you're looking at, and just plug them into the formula. So like I said, this does apply to a ton of real-world situations. Chemistry equations, for example, calculating human population growth, and the biggest one that I can show you is something that's all over the news right now, and that's COVID-19. The way viruses affect populations typically follows exponential growth and decay models. You saw above that for the growth model, we used a value of 3 for b, and b can also be used by tons of other letters, and in the case of viruses, they tend to use r. So that initial 3, that's called the r naught, or r at the initial stage. The higher the number that r or b is, the bigger the growth is.
Tell them what an R naught of 2 really means, Dr. Cheever. Teach them some math, No? I'll do it. On day 1, there were 2 people with it, and then there were 4, and then it was 16, and you think you've got it in front of you. But next it's 256, and then it's 65,000, and it's behind you and above you and all around you. In 30 steps, It's 1 billion sick. 3 months. It's a math problem you can do on a napkin. And that's where we're headed.
That's why the phrase flatten the curve is so important. The less people infected initially, the less devastating the disease is. A lot of people at some point, myself included, said we'd never use certain math concepts, and obviously that's wrong. So I hope you guys learned a little bit about exponential growth and decay, and for more information, us GEARUP tutors are always here to help you guys with anything you need. Until then, stay safe, and we'll see you soon.